we're kind of going to talk about MRV, but we're also going to use this session as kind of a way to abate some of my worries about the various CDR technologies. Some of my worries, some of the worries that I've heard from various people who I've spoken to about this, some of the worries that the panel have shared that they've heard, worries, concerns, misconceptions, and we're going to just try and breathe through them in this session. I'll be voicing the worries, and our panelists will be bringing the science for trust. That's the general idea. So just to start us off, I'd like to kind of ground us in where we started in that first session by asking each of you to kind of talk very briefly about the reality of where we are with your technology right now, here, June 2024. How far are we from where we need to be in terms of carbon removal? What stage are you at, sort of proof of concept, research, delivering CDR, and keeping in mind the recent publication of the second edition of the State of CDR report, which is a really wonderful resource. Can you just ground us a little bit on where we are right now? Let's start with you, Anna, if that's all right, looking at marine CDR.
Yeah, happy to. So I think, first of all, it's really important in the MCDR context to differentiate between the different many approaches that all fall under MCDR. So we obviously have the biological approaches or more biologically based approaches like biomass sinking and enhancing the biological carbon pump. But then we also have the more chemically oriented approaches like ocean alkalinity enhancement, direct ocean removal. So even within that category, there's a lot of nuance and a lot of different elements to observe. At Carbon to Sea, we are focusing primarily on ocean alkalinity enhancement, evaluating whether it's safe, efficient, and scalable. And if so, how can we build and enable a sector that is trustworthy and responsible? And we do look at MCDR broadly as well, but started off with ocean alkalinity enhancement. So maybe I can focus a little bit on that side. I think right now in the MCDR space, we see we see a handful of really inspiring companies kicking off and doing field trials and doing pilots. These are in the hundreds of tons removal scale. It's extremely small quantities, I would say, and it's, in my opinion, the state of MCDR at this point in time is that we still have a lot of science to do, but we also cannot do the science without doing deployments. It's a really important interdependence, and that's what we focus a lot on at Carbon to Sea, doing the necessary field research to understand what is safe, is it working, and that's, in my opinion, where MCDR is at right now. We are in the low hundreds of tons of potential removal, and we have a lot of science to do.
Great. So at the pilot stage,
yes,
low hundreds of tons, lots of science coming. Love it. Thank you. Ondrej, could we move on to you and biochar, please?
Okay, so I'll start with the CDR report that was released just about 10 days ago or thereabout. And it very nicely shows, I wish I had some of the beautiful graphs that the report contains here to show, but for those of you who have seen it, you will know what I'm talking about. For those of you who haven't, please go and see it. So it shows the scale of the CDR, which is quite large, but if you look at the novel technologies, and biochar and a number of the other technologies we have here on the panel fall into that category, they are still a very tiny, tiny sliver of that overall contribution. So we clearly have a lot of space to fill with these technologies to improve the removal. So going beyond afforestation and other much more established technologies. Now, where biochar sits in that is sort of in the hundreds of thousands of tons of biochar produced globally per year. So it's, I would say, beyond pilot scale, but it's by no means at its full potential. We are still starting, so there are about 150 or 160 companies producing biochar in Europe on the few thousand tons per year production capacity. So that's good. These are not laboratory tests or so. These are commercial facilities, but we can go bigger, both in terms of the numbers of the plants, but also the scale of individual plants. So there are different ways to progress there. I think we are it's interesting to see where we're also in the stage of the research. So I've been doing research on biochar for the past 15 years or so. I think we are past the stage of the basic research. We've proven the major concepts, and I think we'll be tackling some of the questions here later on in the panel. And we are moving to a different stage of the research. So it's not that the research is over and we know everything about biochar. There is still plenty we don't know, or plenty we can improve our knowledge on. But we are now at the stage of deployment and scale up, and the research should be supporting that.
Great, thank you. So we've got more commercial offerings in the biochar world, and scaling up is the name of the game.
Yes.
Great, thank you. Pascal, enhanced weathering.
Yeah, thank you for having me. I think enhanced weathering is at a similar stage, actually, where I think what's been established is that it has great potential in terms of gigaton, multi-gigaton per year potential, low cost at scale, imminent scalability as it piggybacks on existing infrastructure. Great co-benefits could have been established over multiple years of field studies now for farmers in the environment. Companies have started scaling up. So Lithos has been mentioned on the panel before, $57 million, $180,000 delivery over the next 4 years. So companies have started ramping up volumes. Also not yet commercial scale and actual climate impact, but they're starting. The biggest barrier to even more scale at the moment that we see is that measurements, like we've heard before, the quality bar is rising on MRV. And so we can measure it. If you want to do it great, you need to really have a lot of tedious manual sampling effort that gets expensive very quickly. And so that's what we set out to solve with. Everest has developed a novel sensor that allows our customers to very directly in the field measure additional CO2 export much more cost effectively and scalably. And we have validated that now we'll have commercial pilots with first customers in the next few months, and then scale up the technology next year to solve enhanced weathering's measurement challenge.
Great. So lots of potential and working on how we measure it. Thank you. Helen, I'm going to come to you. You're not here necessarily representing a carbon removal technology, but maybe you can speak a little bit to the big picture of the market of where we are right now, and particularly just picking up on something that Ondrej said that's very obvious in the State of CDR report, that the novel CDR approaches are just a tiny slither of the big picture right now. Can you talk a little bit about that?
Yeah, thank you. And just first, I'd like to explain what Puro.earth does so that everyone's clear. So we're a carbon crediting platform focused on durable carbon removal, where the carbon dioxide is stored for more than 100 years. And we have 5 methodologies, which are all familiar to you. So biochar, terrestrial storage of biomass, enhanced weathering, carbonated materials, bioenergy carbon capture and storage, and direct air carbon storage, which we've heard a lot about today. I hear an alarm. Is that a test? I'm safety trained, so I just want to ask. Sounds like it's gone. Good. And we're now investigating the ocean environment as well. So I'm super excited to be here, and it's hot, but we're all focused, so this is good. Let me share. So, we have scientists who write the methodologies. We have an independent advisory board that signs them off. We issue carbon credits that have been independently verified after the removal has occurred, and the life cycle of the carbon credit is published in our registry. These are the 3 really important pillars. Now, you mentioned a marketplace. We used to be a marketplace, but are no longer focusing on that. As we've grown. Our core platform is around methodologies, issuing credits, and the registry. So over the last 5 years, the ecosystem that we work with has removed around 750,000 tons of carbon in every continent of the world, apart from Antarctica. And each year we've grown, our suppliers have grown, and this year we have issued double the amount of carbon credits in the first half of this year than we issued in the whole of 2023. And we have well-known customers like Cartier, Shopify, Microsoft, thank you, Microsoft, Snap, Swiss Re, BCG, Dropbox, Virgin Airways, ThyssenKrupp. Just to give some examples, you can see all these in our registry. And, the State of CDR, it talked about how since 2021, novel technologies were around 660,000 tons per year, doubled in 2023 to 1.35 million tons a year. But as Ondrej has said, it might have doubled over the last 2 years, but we're still way off where we need to be. So to be clear, we see suppliers, really exciting suppliers, and being here today, I've been talking with a number of them, that are bringing projects to market. but what we need is more customers to buy the carbon credits to build that demand. And that's what we're hoping will match the supply that we see in our funnel for the years to come.
Thank you, Helen. Thank you, everyone. That's, I think, a good sort of setting up for moving forward. So let's dive into some of these concerns that we've discussed about the various technologies of CDR. I think in general, the sort of broad things that people are always talking about, will the cost be prohibitive? Will this be able to safely scale? And then, of course, how do we measure it? So as we go through the more specific questions, those are kind of like general worries that are floating around in the background. I'd like to start with biochar. So biochar seems to be having a bit of a moment right now. Everyone's talking about it. It's delivering CDR, which is great. Here are some questions that have come up for me that hopefully you'll be able to bring the science in to calm my worries. So the big question around biochar, does it actually improve the health of soil?
Okay, so I'll give you a typical scientific answer. It depends. So just like any product, whether it's a soil product or other things, if you put the right product in the right application, it will work well. If you put the wrong product in the wrong application, it won't. So biochar is exactly the same. There is no reason why it would be any different. So depending on what it is that you want to achieve with the application of biochar beyond the storage of carbon, so I think that's sort of well accepted, that if you have the right type of biochar, you will store carbon for a very long time. If you are trying to improve the soil, then it depends on what it is that your soil is needing. Is it improving the physical structure? Is it something to do with the chemistry, the biology of the soil? What is it? And then certain biochar will be able to do that, other biochar won't. So it really depends. So if you are after water retention, you will need to have a biochar that works for your kind of soil. Is it a sandy soil, clay soil? What kind of soil it is? And if you are after nutrient management, maybe one thing to sort of dispel is a common misunderstanding that biochar is a fertilizer, and it isn't. Most biochar isn't. So it's, again, not to say that there can't be a biochar that's a fertilizer. It's possible if you produce it from biomass that has a high content of nutrients, but most biomass doesn't. Nothing like a commercial NPK fertilizer. So biochar is not a fertilizer. It can be a component of a fertilizer, or you can enrich it in a fertilizer. Then it becomes a fertilizer product, but biochar as produced from most biomass is not a fertilizer. However, because of its ability to interact with the water, with the nutrients and the soil and microbes and so on, it can interact with the fertilizer delivery. So it can help to retain fertilizer in the soil. It can improve the delivery to the plant roots where it actually matters, rather than letting it leach out of the soil and being carried away into water courses and contaminating the water. So these are just a few examples of how it can improve, but again, it really depends on what it is you are trying to achieve. So there will be things that you can't do with biochar. It's not a silver bullet that solves all the problems.
Yeah. And when we talk about soil health, my understanding is that a lot of the biochar production and research and pilots are happening in Europe or North America, where soil health isn't necessarily a biggest concern. In other parts of the world, soil health is much more of an issue. Is it that biochar could be much more impactful if we take it to various parts of Africa or Southern Asia, for example?
Okay, so first I'll counter a little bit the argument that soils in Europe don't need improvement. There is a recent report on the state of soil organic carbon in Europe, and it clearly shows that, especially in Southern Europe, there is a huge deficit. There has been a lot of loss of organic carbon with the intensive agriculture, and now also with changing climate. So soils in Europe definitely do need to be improved as well. They would benefit from biochar application. Again, I mentioned water retention. That's becoming very important, again, in the southern climates, even in Europe. But, of course, there will be countries elsewhere in the world that would benefit, some of them possibly even more, because the soils are even more degraded. And unlike in Europe, the biomass production potential is much higher in some of these countries because of the climate and what is available. So yes, there is potential everywhere. I would refer to a paper that was published at the end of last year that did actually a survey of the potential of biochar in different countries. So if anyone is interested, contact me. I can send you a link to that paper. And it shows what the potential is in each individual countries. unsurprisingly, the biggest potential is in the countries that are largest in terms of area and biomass production. So that's China, Brazil, and the United States. But if you look at the potential of biochar to reduce carbon emissions in individual countries, then that distribution looks different depending on the emissions of those countries. And it's not necessarily those top 3 because of the high emissions from in China and the United States. So other countries, as a percentage of their national emissions, they can make a bigger difference using biochar because of the amount of biomass they have available.
Could you talk to us a little bit about the measuring process of understanding exactly how much carbon is being stored in biochar and how long that lasts if we're using it?
Okay, that's a very good and very pertinent question. There is a lot of discussion, a lot of things going on at the moment as we speak. As you know, the EU is working on a CRCF framework for the carbon removal credit, and there is an intensive discussion around that, and more widely internationally as well. The science of the biochar permanence has been there for a very long time. I remember, I'm not going to mention names, but a famous researcher in the area some 12 years ago at a large event said, well, hopefully we can put this question of biochar permanence behind us and focus on the other things. Well, we are here 12 years later and we are still tackling the same questions, but I think we are getting a little bit closer to having an agreement on a solution. So there are 2 different ways we can approach this. One is similar to other methods where you go to the field and you measure how much biochar you put in. And that's quite easy. You know what you put on the spreader and you apply it to the soil. And then you can come back later, 1 year or 2 years or 10 years later, and take core samples and measure how much carbon you have in the soil. Now, the problem with that approach is that biochar tends to be move around, both horizontally and vertically. So it can move in the soil profile. It can also move vertically. So it doesn't necessarily end up after 10 or 50 or so years exactly in the same place where you applied it. So if you go back to the same spot, you will not necessarily find it. Not because it has degraded into CO2 or methane and went back into the atmosphere, but just because it has moved either further down in the profile or it might have moved horizontally elsewhere. And that would be a problem. So if you use that method for accounting, you will say, well, my biochar has disappeared in 10 years. It has no stability at all. So the other approaches, and the one that's more favored, and I think for a good reason, is to actually measure the permanence of the biochar itself as a material. And if you can be confident that that material does not degrade, or a certain fraction of it doesn't degrade, you can then use that for the accounting. So it doesn't matter where it has moved, if it's now instead of the top 20 centimeters of soil, is now 1 meter down in the soil, or if it has moved somewhere else onto a neighboring field, or even if it ended up in a sediment in the ocean or so, as long as it's stored as a solid carbon, that carbon is there. It's not in the original location, but it's somewhere else. And so you base it on the understanding of the permanence of the biochar. And that's now the question is, how do you measure that? There are various methods that are proposed, and I mentioned the CRCF discussion. So that's one of the discussions there is sort of what methods are acceptable for that. And it looks like the conclusion will be that there will be multiple methods that can be used, which is great for the industry because you don't want to be wedded to only one particular technique or method for measurement. If you have several options, then it makes it easier to achieve.
Great. Let's talk a little bit about the process of creating biochar and some of the questions that have come up there. So actually creating biochar as a process, it does release CO2, the process itself, and it requires energy and it requires a constant feedstock. So that feels like a lot of input and like some negative output to get this, one product of biochar.
Okay, so yeah.
Wasn't a question, but
no.
Discuss.
Well, you just gave me a nice topic. I can keep you here for hours. So starting with the biomass feedstock. So yes, that's really the most critical thing. Without biomass, there is no biochar. Okay, so as simple as that. As we heard in the first panel, Richard presented their technology where they work with various waste materials. That's one option. So you can work with organic fractions of waste. You need to make sure that you know what is organic fraction of the waste and what is inorganic fraction of the waste, so you don't account for that as a carbon removal if it's a fossil-derived waste. But then you have all sort of other. You have agriculture residues. You could have purpose-grown biomass as well. You can have residues from forestry and so on. So there is a wealth of biomass. This paper I mentioned earlier, it actually looked at the sustainable supply or sustainably available biomass, and that's how they assessed the potential for it. So these are not just numbers plucked from thin air. It's an actual statistic based on how much biomass is available. Now, there's, of course, competition for other uses, and there will be much higher value uses for biomass than biochar. So, for example, if you can build a furniture from it or a building or so, then by all means do that. Now, there's an interesting question, what do you do at the end of life of these products? Can we actually then take these building frames and other things and convert them into biochar at the end rather than chip them and send them into landfill or burn them? But that's a whole different topic. So that's the biomass feedstock. In terms of the process for it, so the pyrolysis process is a thermochemical process. You heat the biomass in the absence of oxygen to above 450, 500 degrees to get something that you can call a stable biochar, and can be much higher temperatures, of course, depending on what you try to achieve. And in that process, you stabilize a large portion of the carbon that was in the biomass in the solid biochar, but also a large part of it, about 40% or so, goes into the vapors and the gases that are produced as co-products. Now, these tend to have quite a reasonable calorific value, so you can burn these, and typically you would use them to power the process itself. So after starting the process, you need to have some startup fuel to get things going. But once it's running, the process can be fully self-sustained. You might actually be able to export some additional heat and possibly electricity, depending on your process. So the energy consumption is not really a major issue because you can be self-sustained or very close to that. You can also integrate with other sources of heat for pre-drying your biomass, because it's the moisture in the biomass that really is what drives this energy consumption. Now, for the CO2 that's emitted, of course, it would be nice if we could capture that, and there is a nice synergy there with bioenergy and CCS technology, because you could just capture that CO2. And we are now working on an EU project called CSync, and this is one of the things we are exploring, is the synergy between biochar and BECCS technology, so that we improve the carbon sequestration potential even further, because we now have the carbon locked in the solid form in the biochar, and we can also capture the CO2 and do the same thing as BECCS technology would do with that.
Nice, thank you. There are some solutions to my worries, so thank you for that. I could ask many more questions about biochar, but I'm going to move on for the sake of time. Anna, I'd like to come to you and talk about marine CDR. It's often said that we know more about the surface of the moon than we do about the ocean floor. So I suppose a lot of the worries that I've collected about marine CDR are the fact that we are dealing with a complex ecosystem, and a sort of important part of our planet, 2/3 of our planet. To mess with that feels like tricky business. So, could you abate my worries?
Yes, I think you raise a really important point. The MCDR approaches face, I think, an additional challenge to other CDR approaches, because humans care a lot more about the ocean, even though we don't live in them. We care more about the oceans than we care about our soils, perhaps. And we also don't know as much about them. So that creates a very logical, logical reaction to be worried about it. The other thing is that it's, as you said, extremely complex. And I'd like to pick up what you said, that we are messing with our oceans. I think that's the key piece, right? Like, what most of these MCDR, or all of these MCDR approaches, are trying to do is to enhance a natural process. But these natural processes are extremely complex and extremely difficult to explain. Explain to someone what alkalinity is. It's difficult. I've been told many times, and I still probably couldn't do it justice if I tried now. But the point being is that because it's an open and complex system, it has so much potential to scale, much more than closed system approaches have. We need a multitude in all of the approaches, right? But the key is that it needs to be a a diverse portfolio of CDR approaches if we truly do want it to do our climate crisis justice, if that's a weird way of saying it, but you know what I mean. With this increasing complexity of an open system that has so much more ability to remove carbon from the atmosphere in theory comes a large difficulty and challenge of measuring it. And indeed, you cannot measure it 100% accurately. It's not going to happen. The key thing in the ocean space is that it's going to be a intricate combination of models and measurements. But what we are missing today is really grounded empirical evidence that measurement A does indeed imply that X amount of carbon dioxide has been removed from the atmosphere. To put it very, very simply, we can go into so much more detail as we could in biochar, but I think that is one of the key difficulties in the MCDR space, that it's so complex and challenging to explain in the first place. But in principle, we are trying to enhance, by we, I mean the sector, not Carbon to Sea, is trying to enhance a natural process, which has an enormous ability to scale in theory if it can be done safely. And we do know a lot about the global carbon cycles. Otherwise, we wouldn't be looking at ocean alkalinity enhancement, right? Like if we knew nothing about the ocean or about the natural weathering cycle, no one would be talking about it. But we do know, and we do have some evidence that in theory, this is what happens over thousands of years. So there is an ability to enhance that process, and there is some certainty that it might happen. But what we don't know is exactly how much carbon dioxide has been removed if a company or whomever injects X amount of alkalinity or decarbonized patches of water or biomass.
Yeah, I think that's a very good reminder to bring up that, all of the novel CDR methods are trying to, in some way or another, replicate and amplify a natural process that is already actually part of the carbon cycle, and we're just trying to speed it up or scale it up or whatever, which we'll also come to when we talk about enhanced weathering. There's all these natural processes there. So, as you say, in the marine carbon removal space, there are many different solutions, many different technologies that are actually currently being piloted or being researched. And the ocean is a vast space and in some ways a vast resource. So why can't we just say, okay, well, we'll forget about anything to do with our soils and we'll forget about anything to do with enhanced weathering, and we'll just focus everything on oceans, because then it's not our problem anymore. It's just in the ocean.
I have a lot of answers to that. So first of all, I think we are in an urgent situation, right? There are still some questions to be solved in each of these approaches. So we kind of do have to divide our resources between all of them to see what sticks, sort of, and what works. Secondly, sure, the ocean is huge, but find me the resources that could do that. Find all the stone, find all the renewable energy that can alkalize the entire ocean. And thirdly, it's very important, of course, to say that as you also mentioned about biochar, it depends on where you do it. It depends on how you do it. It's not the reality is not that you can just inject alkalinity or grow biomass in the entire surface of the ocean, right? And as we heard on the panel before, the crucial element with marine carbon dioxide removal is that you require the patch of the water where you enhance the capacity to remove carbon. So whether you added alkalinity to it, or you grew biomass that sequestered CO2, or you added decarbonized water, you need that patch of water, if we think of it as a physical 3D object, to be in contact with the atmosphere for long enough to actually remove that carbon into the ocean. That is the actual removal. Now, if you do that in an area where it's, for example, in a subduction zone, so the water from the coast immediately is downwelled into the depth of the ocean, you have not done any carbon removal. We have some certainty, we have some knowledge and some models that can tell us where those very efficient areas are in the world, but the reality is not that you can just do it in the entire ocean. You got to do it in specific strategic areas, and you need to ensure that your water is actually in contact with the atmosphere long enough to actually remove the carbon and then be subducted to the deeper ocean.
Yeah. Just as Ondrej was saying with the soil measurement, the carbon can move around in the soil, which sounds pretty cool, actually. But I can see that happening as more of an issue in the ocean. You know, that's the ocean is kind of one big shared commons, right? So, like, how do we measure exactly our intervention removed this much carbon in this space? I mean, that feels almost impossible.
It is, yeah. I mean, it's not possible, right? To or maybe it is possible. I don't know. Someone can build a
not
cool
possible
sensor.
yet.
Not possible yet. Someone can build a cool sensor that can tag exactly the one CO2 molecule that someone removed, and it's forever tagged and tracked in the ocean, right? But that's why we need the models, right? Yeah. And we need to have an ability to compare and model how different approaches are going to interact over time.
Yeah. And I think the fact that the oceans are a shared commons is part of your point that you know, people seem to for some reason care more about oceans than they do about soils. Yeah. I think people really feel the impact of, you know, if somebody does something in the Gulf of Mexico, it can affect people in the Mediterranean, and then people do things in the South China Sea. You know, that it feels much more fluent and it feels much more communal. And that may be part of the reason why people are a bit skeptical of, you know, messing with the ocean when it comes to CDR.
Yeah. I think another important point is that one of the when we talk about MRV in the ocean in particular, I actually like to separate it into just the M, because really we're talking about the M and not about the R and the V in that particular challenge. It's the modeling and the monitoring and the measurement. And we have currently in the ocean space, we are kind of conflating often, I think, the kinds of measurements that we are doing for environmental impact monitoring, which is very different from the kinds of measurements, the ways of measuring, the frequency of measuring that you do for quantification of the actual carbon removal. But also there's this like requirement and expectation from the broader public to like show everything that's going on and to show all of the data, and to it feel, because it's a shared common, it feels like the data that's coming out of a removal process or of an monitoring company should also be a shared process. And it's a huge challenge because we don't have the types of sensors, the types of monitoring solutions that is required for a truly scaled up MCDR scenario. We have extremely good, extremely expensive sensors that can do it on a like regional or even global basis, but those are not going to be serving companies that need project level monitoring and accounting. But if you require all of that data to be public, I personally don't have an opinion about this, right? Like I know we need that data in order to advance our science, but it's a dichotomy. It's a problem because we are expecting innovation, but also we're like expecting all that data to be available to everybody. And I think there's probably some time where that can be the situation, but at Carbon2C, for example, we're funding a lot of the foundational science to assess whether it's efficient and safe and scalable in the first place, but we're also working on the right structure and thinking about the enablers that can then eventually become a truly trustworthy and responsible market. And there's maybe some time in between where you have to share a lot of data, and eventually we need to think about how our company is actually going to be operating at scale. I don't know that we really have that infrastructure in place.
Thank you for that. Lots of interesting stuff coming up, but again, I'm going to have to move on. Let's talk about enhanced weathering, Pascal. So it doesn't feel like a natural occurring thing that we're enhancing, but that's just, like a sort of gut instinct that we're kind of like doing something that feels like a chemical addition to soils or rocks or whatever. And that in itself is kind of a worry that we're somehow altering the natural system. Tell me I'm wrong.
Yeah, that's actually a common misconception, if not the most common misconception that we've heard from people throughout the ecosystems. And we've heard a lot about soil health before, and that was great. And a lot of that applies to enhanced weathering as well. It's always a nuanced answer to it. But what I wanted to add to that is just a bit anecdotally almost, but applying rock dust to fields is actually a very natural thing that farmers have been doing for very long times already. It's called ag liming. It's a very common practice in agriculture to apply crushed limestone or basalt, typically limestone, if you have it available, and that would be in most parts of Europe, for example, or basalt, which we've also heard before is one of the most common minerals in enhanced weathering. It's a very common practice in Brazil, for example, as a natural material to prop up soil pH for optimum plant growth. That is particularly important in regions where soil pH is rather low and crops have an optimal growing pH, so you apply some crushed limestone or basalt and crops have their perfect environment again. With silicate rock like basalt, you also have additional nutrients, macro and micronutrients that all plants need to grow. You improve water retention capacity of the soils and further aspects more. So it's actually something that farmers that actually are in touch with those soils and the environment every day have been doing for a long time already.
So if farmers have been doing it for such a long time, what makes this sort of like current and innovative?
Well, it's now being applied with silicate materials that do not yet contain carbonate on it. Limestone, for example, is calcium carbonate. There's already CO2 molecule on it, so you don't get the same CDR as when applying silicate rock that is only silicate and not carbonate. So it's additional CDR through a different rock that does not yet have carbonate on it. They also apply it in slightly higher doses to actually generate more of per area, and then measure it and really pay for the rock to be applied. So that's why farmers are actually excited to participate in these projects as well. For them, it's a free natural ag lime replacement that they can use. But it's now really being applied with the right materials at the right dosages, and the project developers that we are working with are actually going above and beyond to optimize for pharmacobenefits as well. So from that perspective, I think it's a win-win-win.
And when it comes to the measurement, presumably you have some of the same challenges as Ondrej's already pointed out with biochar. What keeps you hopeful in the measurement of enhanced weathering?
What keeps me hopeful there? Well, we are commercializing a measurement breakthrough that will unlock the space, I would say, in the short answer. To give you some more context on that, and I think enhanced weathering has both parallels with biochar and ocean alkalinity enhancement there to some degree. What companies are currently doing, and that is part of the deliveries that I'd mentioned at the beginning at the moment, is a very tedious manual sampling schedule, taking both solid soil samples to measure how much of the feedstock has dissolved, but then also taking liquid samples from the field to measure how much additional carbon do you have in the water that is flowing out of the field. It works if you're willing to pay top dollars and pay for the expensive equipment and techniques and do it at scale, but I think it will be really hard and increasingly harder to really scale. And so that's what we set out to solve. And to give context for that, just a quick pull-up, and I'm going to try to actually explain alkalinity, how enhanced weathering works. What people do is they spread silicate rock dust on fields. That rock dust contains cations. Additional cations after mineral dissolution in the soils will lead to more CO2 from the atmosphere dissolving in the water in the soils, counterbalanced by the cations in that soil pore water. So you get additional bicarbonate and carbonate, short carbonate alkalinity. And ideally, what you would want to measure to get perfect evidence of CDR through enhanced weathering would be to measure that additional carbonate alkalinity efflux across your whole field and continuously over time. And then you do that in a control field and a treatment field to compare what delta do you get by applying minerals. Now, measuring across a whole field is obviously not realistic, not really feasible. And we also don't need to do that because statistics tells you if you take point-in-space samples and measure continuously with very high accuracy, then you can approximate that overall measurement of the whole field to a very good degree. And you have a statistical framework to actually calculate the uncertainty depending on the number of sample points you have. And then the field heterogeneity, so the variance in your field, will tell you how many samples you need to approximate that overall field measurement very precisely. And so that's exactly the breakthrough that we are developing now. We have developed a sensor that measures continuously that carbon alkalinity in the field at very high accuracy and much more affordable. So we want to enable our customers to place sufficiently many of these devices in their fields to get a really highly accurate measurement on the field level. Yeah, we've tested it with high performance in the field, have run first field tests, as I mentioned. Next month will now be commercial pilots with initial customers, and then next year we're ready to roll it out.
Great, thank you. We're running out of time, but I must speak to Helen about this, the importance of this building trust. We've heard a lot of the kind of answers to the worries, the science around the measurement, and some of the things that we're not yet able to do, some of the things that we are able to do when it comes to measuring. What can you tell us from the perspective of the broad market of why all this is so important and the importance of building that trust?
Yeah, I think it's important that we've talked about the different techniques and all the different pros and cons, but when you're looking at carbon removal credits, the credit that comes out that's based on the accounted for carbon removed from the atmosphere, these projects are independently verified. And that's really, really important, because without that, you haven't got anyone who's checking, has that project follow the rules or the methodologies, as we call it. So that's the first thing to bring into the room. I know it's very basic. And I think, when we're looking at how do we ensure everyone adheres to standards and what's out there, we're a learning organisation, and today we've just issued an update to our geologically stored carbon methodology. And we did that with our ecosystem and with scientists, and it was signed off. But why did we do that? Well, we did that because the Integrity Council for the Voluntary Carbon Market, the so-called ICVCM, sets a global minimum benchmark. And we have applied for that and really wanted to make sure that we could meet those requirements. So you're starting to see a market whereby you have got international voluntary rule setters, as well as regional governments. You mentioned the EU's carbon removal certification framework. So you're seeing governments come in, voluntary rule setters come in. And so that really helps us as a carbon crediting program make sure we're meeting those minimum requirements. It helps build trust, and everything that we do is transparent. So all the methodologies are on our website, all the carbon credits that are issued are on the registry, and all the projects have all the details behind what they publish for each project. So transparency equals trust, but also building these minimum benchmarks. And then I think, just to sort of go back to what we did, so when we looked at updating our geologically stored carbon methodology, we look at the eligibility criteria, what type of carbon dioxide should be allowed to be credited, how can that be aligned with net zero pathways, how long is the crediting period, is it from 5 years to 15 years, and we put down a lot more detail around how do you quantify, how do you do your life cycle assessment, and how do you demonstrate that what you're using is sustainable. So all these things are really important as we move together and build trust. And then finally, on the point around standards and trust and transparency, we call on governments to set strict criteria on what is a high-quality credit, and then to partner with us to deliver the net zero emissions. So just a few examples there of a very fragmented, moving landscape, but how we operate within that.
And given it is so fast-moving and growing exponentially, as we talked about with the recent State of CDR report, presumably standards and regulations and measurement all have to be dynamic enough to keep up with whatever might come next, or the scale that we're moving at. And that in itself causes a bit of friction, I imagine.
Yeah, you constantly need to update your methodologies, because we talked about the science is changing and what you guys are doing is developing. And so that's why we have scientists who do that, and we consult, and it's all publicly available, and it's signed off by an independent advisory board. And then within that framework, you've got the United Nations framework on climate change, looking at rules. You've got the EU, you've got the UK, you've got Singapore. So it's all starting to coalesce together. And a lot of what we do as a carbon crediting program, which is also called a standard, and it's also called a registry, we like to make it complicated with lots of different language, is bringing that together. What does that mean for our ecosystem? How can we help our CO2 removal suppliers navigate that really complex, nascent field as it develops?
And also presumably the kind of translation from the science that's happening on the research level, the like hands-on carbon removal that's happening, then the regulations, and then like public perception. All these different things need to like understand all the different parts that are moving, and that in itself is like a very dynamic system.
Yeah, we always look at it in terms of sort of 3 pillars. I can't cope with more than 3 things. So how is the certification being developed by the governments? How can corporates use carbon credits, so the claims that they can make? And then, longer term, how will that develop into compliance carbon markets? We mainly operate in the voluntary carbon market. We've applied for CORSIA, which is an aviation compliance market, lots of acronyms. So as voluntary carbon markets and compliance carbon markets starts to coalesce, how does that compliance pillar? So certification, claims, compliance, that's how we try and frame it.
Thank you very much. I'm afraid we're going to have to wrap up. Final sentence from each of you, if I may, just to end on a nice note. What keeps you hopeful when it comes to CDR? Anne? 1 sentence, please.
In terms of MCDR, I'd like to copy the previous panel, the partnerships and the pace at which both academia and the private sector are currently working together in MCDR on a very sound basis keeps me very hopeful.
Thank you, Anne. Helen?
This ecosystem and the fact that around 140 governments have set net zero targets. Think back just 5 years ago to 2019, there was only a handful. That keeps me hopeful. And the fact that we will deliver the net in net zero emissions.
Putting the net in net zero. Thank you. Pascal?
Yeah, I'll keep it short. I think the influx of talent and investment, both from governments and investors, to really drive this and drive the innovation that we need to achieve the necessary scale.
Thank you. And Ondrej, finally, what keeps you hopeful?
The level of activity and energy in the area, especially in biochar, and the opportunity space for biochar application in so many different applications.
Thank you very much. Thank you to our panel.